Well, good morning, everybody. Pleasure to be with you, and even bigger pleasure to introduce superstar here. I'm surprised he's going to perform with such a small audience. He has asked me to give a personal introduction. He's very proud of the fact he was just described as the Lady Gaga of physics. And so please join me in welcoming.
It was described not by Salman but Epstein, you know, found in 3 million pages. One of those was found there. Okay, jokes aside for the moment. Okay, let me tell you a story about graphene. I have given probably 7 or 8 talks in Iraq, but I realize that I have never spoken about graphene before this audience. Very, very surprising. So I'll give a talk which is kind of for broad audience, public lecture and mixture of science and public lectures. So very lowbrow talk. Just for material scientists like Tony. So let's start with an observation. If we deal with materials, whatever you have in the lab, usually all the materials have height, length, width, and etc. We live in three-dimensional world, and everything around us, including materials, are literally three-dimensional materials. You won't find materials around which are two-dimensional or quasi-two-dimensional materials which have no one of those parameters, for example, thickness. Why it is so? It's why it's not plain. Yeah, it's plain now. So essentially, to grow material, whatever, you know, you need temperature to put 2 atoms together and 2 molecules together. When temperature is there, vibrations are there, and vibration destroy order in 1 or 2 dimensions. So everything, because in three-dimensional world, everything tries to have a three-dimensional architecture, and there seems to be no way around to this. You can't grow materials in 1 or 2D. But you can think about Gedanken experiment, in which we know that materials have rows of atoms and planes of atoms, and you can ask yourself a question which we asked about 25 years ago: can you extract an individual atomic plane? And this doesn't contradict those powerful theorems which forbid the growth of low-dimensional materials. It's in principle allowed, because the material itself grown at high temperature, where the growth is forbidden, but if you cool it down sufficiently to room temperature, there is nothing wrong with having material extracted out of those. So that's the experiment we have done in reality, and we started with graphite. Graphite, because it's a very high melting temperature material, 3000 centigrades or something like that, where it smells at room temperature is 10 times less than that, so vibrations are not essential, and the experiment is essentially very simple. You put a scotch tape on top of graphite and peel it out, and there are those flakes which stuck to the surface of the material. If you take a microscope and look at microscope in the transmission mode, you'll see that some of those flakes are really black. So light is not coming through, but other flakes are transparent. And it was kind for me a eureka moment, because graphite is a metal, and pretty good metal. relatively speaking. So if a metal is transparent, it means it's very thin metal. And I know from my experience that some of those most transparent flakes are 1 nanometer thickness, okay, 5, 6 layers, something like that. So, and materials, when I saw this image 20 years ago, I know that materials are kind of 1 nanometer thin films is essentially impossible to produce in any means which we normally use, evaporation, deposition, and so on. It's interesting to know that this is Scotch tape and graphite is very common materials. Anyone who ever worked with atomic force microscopy, you get a microscope and you get a piece of graphite, and the instruction tells you use Scotch tape to make a fresh surface and then to check your resolution, which should be atomic resolution of your microscope, STM or AFM, with graphite and clean surface. So people done thousands and thousands times in 1,000 groups around the world, use Scotch tape, thrown away the Scotch tape in a little bin and investigated what happens with the surface of graphite without realizing that they probably threw away their Nobel Prizes together with this piece of Scotch tape. So that's essentially what we have done 20 years ago. This is how graphene, a monolayer of carbon, looks like when it put on silicon oxide wafer. Its special thickness in order to increase the contrast, it's 1 millimeter, and it's monocrystal, and it's only 1 atom thick. You can use modern technology like transmission electron microscope to prove that it's a monolayer. Not many people believe that at that time, but it's a monolayer. So people sometimes ask what's so special about graphene, why people make such a hype about it. Scientifically speaking, in my opinion, the most interesting thing about graphene that it's very existent in our world where we live at finite temperatures, 300 Kelvin, and there are all those vibrations, and this material still exists despite presence of oxygen, air, whatever. If you try to make the same feed with, for example, platinum or gold or other materials, it's impossible to do. If you evaporate, try to make a gold film, for example, thinner than 100 angstroms, 100 atoms thick, it would melt at room temperature completely, or other films will be oxidizing, not so melting. So, if it would be the end of the story, just existence of two-dimensional materials, 1 atom thick materials, I wouldn't be speaking today. It would be scientific curiosity, I would say, because it looks like a very simple structure, just carbon atoms in this honeycomb lattice and so on. So what came as a discovery rather than kind of logical sequence of trying to do is how that discovery, I use the word as a word because no one expected, no one predicted a lot of different properties where the material is kind of superlative to other materials. We know it's the strongest, it's the stiffest, and so on. The list is long, and it's still people add up some adjectives to this one. You might be surprised, but the Nobel Committee gave the prize not for the list, they gave, in my opinion, the prize for kind of electron properties of graphene, 2 or 3 lines out of this list, because electronic properties turned out to be quite unusual. But for me, which has become obvious over the last 10 years, it's the most important thing about two-dimensional materials is how they are different from their parent materials. Because if you take a small piece of the material, you believe that properties would be similar to a bigger counterpart. It turns out to be completely not true. For example, graphite is a soft material, poorly conductive material. Graphene, kind of a descendant of graphite, and is to be stiffest, strongest on nanoscale material, stronger than diamond, and it's also much more conductive than copper. Very little overlap between properties of three-dimensional materials and their siblings. So that's what I spent a few minutes trying to give an idea of what the Nobel Prize was given for. And this is very unusual science, which is about electronic properties of graphene. I didn't put any formulas in my talk, so I'll use, no, there are a few. I'll give you an idea what it is by showing this cartoon. When we are talking about metals or semiconductors or material science, electron waves inside are usually described by like billiard ball model, electrons moving like bullets, or more accurately by Schrödinger equation with some extra terms around this. This is material science, condensed matter physics. When we're talking about particle physics and accelerator physics, astrophysicists and particle physicists, they like another equation, which is a relativistic analog of Schrödinger equation. When particles are close to the speed of light, it's so-called Dirac equation, and it's kind of very different equation, so communities don't speak much to each other. And where graphene comes from, being a material science object, and nevertheless electrons there mimic what's happening in ultra-relativistic world when the particles moves close of the speed of light. It's not true, it's not speed of light, it's a mimic of what's happening in the relativistic world. So in a sense, what we got a possibility to study relativistic physics on a desktop, essentially, so which make happy not only condensed matter community dealing with electronic properties, but also particle community, that some of their phenomena which they couldn't possibly in 1,000 years to probe at CERN or other accelerators, they can probe them in condensed matter experiments. And I'll give you, this is probably one of those examples, which is again explained in cartoon. About 80 years ago, Klein at, I think, Swedish or Norwegian theoretical physicist discovered theoretically a phenomenon which is called Klein tunneling, and you know what happens with the car. You also know, from your own lectures, many of you, what's happening if you talking not about real world, about quantum world. There is quantum tunneling, where part goes reflected, and part of the particle wave packet goes through a wall. What is strange about ultra-relativistic world, or the world of electrons which live inside graphene, that however wide or however high you make a barrier, a car which would go along the rules of this relativistic Dirac equation would pass through without noticing this barrier. This is called Klein tunneling, and this is phenomena which is routinely seen in graphene. This is phenomena which comes from relativistic world, which actually explain why graphene is so conductive material, because there are barriers around due to impurities, due to some external potential, and still electrons, according to this Klein tunneling, do not notice this scattering, which allows see many quantum properties quite clearly in this world. Another example, okay, just to show that it's not a single example of relativistic phenomena, is an interesting example, came also about, okay, whatever, 15 years ago. We were first at that time to learn how to make freestanding membranes, and this is an example. So the central hole is intentionally half covered by graphene. It's bilayer, and what you see on the image, that material, the light goes through, that material is gray, so it absorbs some air, and that was access to this material allowed us to check how light is absorbed by this one. And this has been done essentially by analyzing optical image. And what you find out, that each layer of graphene absorbs 2.3%. 2.3% seems to be a random number, but if you are a condensed matter physicist, you always use some analysis, and the analysis tells you that it's 2.3% not a random number, it's pi multiplied by the fine structure constant. And this is kind of intuitively expected, at least was expected for me, because what you probe in this experiment, you probe coupling of light, which is electromagnetic wave with relativistic kind of charges, and this coupling is described by the coupling constant, of course, which is also known as fine structure constant. So if you ever see a piece of graphene, so remember that with your naked eye you can probe one of the most mysterious constants in the universe, 1/137. No one knows actually why the number is so, but this is one of those cute things which you can send about graphene. So there are many other examples, but of what you can or cannot do with graphene. That's probably, I'll skip this one. It's about how we wanted to save the world from water crisis. I got an international prize for water for this part of the research from Saudi Arabia, actually across the Gulf from here. Let me show you that graphene still very hot material. This research was done couple of years ago together with my Chinese counterparts, Yan Su from Shenzhen, and I called it graphene as the philosopher's stone. It's not from Harry Potter. It's more like what originally the philosopher's stone was. So people try to find a material which changes some rubbish into gold. And in our case, rubbish is e-waste, e-rubbish, which you mostly familiar with when you throw away your computer. So we took literally some of this rubbish, dissolve it into an acid, and we get a transparent liquid. And now this liquid, which contains all sorts of salts, we pour it through a collection of graphene flakes as a filter. It's very important that it's not graphite. Graphite doesn't do this. You need to have 1 or 2 layers of graphene, then you get this trick. What you see, the color of the membrane changes from black, a characteristic of graphene, into gold. Then you take this membrane and burn it in air and you get gold. So gold is extracted selectively and very efficiently by this material. So all other materials, nickel, copper, and everything else with there goes through its selectivity with respect to gold. This is one of those things which again emphasizes that graphite is probably most inert material, more inert than Teflon, PTFE, but unlike three-dimensional counterpart, graphene is essentially catalytically active material. We do understand this day why it is so, well, people trying to utilize this commercially, this technology, using not aqua regia, but some other solvents to recycle waste. I spend my next and last 10 minutes to go beyond graphene. It's already known for 20 years. Our second paper was essentially saying, and I think more important paper was saying that graphene not alone, there are other materials which you can extract the same way as graphene, grow three-dimensionally and then extract an individual atomic plane. This is 2005. I think it's more important than the first paper. And we now know about, few hundred of counterparts. Some of them are well studied, like boron nitride, graphene oxide, fluorographene, dichalcogenides, other oxides are very popular as well, but essentially people try to use those materials to find out some interesting and useful properties which can be utilized one way or another. That's what can be called graphene 2.0, and then graphene came up in yet another reincarnation, if you wish, graphene 3.0. In this case, because we have library of different materials, low-dimensional materials, you can think about making this kind of out of individual planes, this kind of heterostructures, or build up designer materials back, disassemble something into individual planes and then assemble again. This is very hot area of research. You can consider it like LIGO on atomic scale, still goes on and on. Why do we do this? This is kind of an example that we can really do this, not only the cartoon, but in this case it's superlattice of graphene boron nitride. But why we want to do this? It's relatively simple structure which we assembled something like 10 years ago. One of the first, if not the first, heterostructures made by this. So there is a semiconductor molybdenum disulfide in the middle. There are insulating materials, boron nitride, and there are 2 layers of graphene you can vaguely see over there, and then you apply voltage, inject current, and you get light. So what you get, a rather efficient LED, the same LED as helps to project this image on the screen. The difference is that it's flexible and transparent, at least potentially. So I'll touch it why it is important, but in particular, but essentially with this assembly you can do what semiconductor microelectronics industry has been doing for the last 50 years with kind of other materials. So you make all kinds of assemblies in this way. The last 5 minutes of my talk, I like to touch, which I'm fundamental scientist. I don't do much applied research, but still do some applied research occasionally. It happens. But even in the community who are dealing with graphene, there is very information about how graphene has already coming into consumer products. It's so thinly spread that people do not know about this. So it's in literature, it's often journalists blame or wonder material when we will get something out of this material. In fact, material for first 10 years, it was impossible to obviously to speculate. Well, people, of course, speculated, but you don't expect to do anything with scotch tape and piece of graphite. You can't imagine people do this in China or Vietnam by using scotch tape or anywhere else in the world. But occasionally, 10 years later, people learn how to make graphene en masse and in tons and square kilometers if it's required. This offer has caused the demand from the industry, and industry start using for all sorts of applications, and there were thousands of applications my colleagues and others came up with. So it was the same as in Silicon Valley, fake until you make it. So the same was referring to the research in academia trying to speculate something. But then during the last 10 years, consumer products had started appearing where graphene has been used. For example, this had skis, they're called graphene skis, somewhere there. And this watch from whatever, Richard Mill, watch costs about $1 million. Dollars, and skis very expensive, but graphene is there. It doesn't improve anything except for the price of those products, in my opinion, but other products like shoes, helmets, it's a little bit improved. It's very widely used for cooling, for LEDs, and if you have Huawei, it's routinely behind the screen there is a thin layer of reassembled from graphene, from monolayers, assembled graphitic film which cools electronics. The biggest application at the moment out of many essentially in lithium-ion batteries, which if you have an electric car, consider yourself as a proud owner of about 100 grams of graphene, because Cattle, this is the biggest manufacturer, and other manufacturers at BYD and etc. They use graphene to improve conductivity of both anode and cathode in these batteries. It doesn't do much, but it gives you 10, perhaps 30 miles of range on your whatever 300 range of there. So it has become a routine in battery industry together. Another development which is going on is about adding graphene to tarmac, to asphalt. Allegedly, people claim that it's improved the durability of asphalt by a factor of 2.5, and the costs go up only by 20%, which is good. Paint, graphene improved paint is also a big business. No one knows how it works either for asphalt or for example, paint for ships, but this is a company called Finlines. They tried to paint their ship, one of those ships, with graphene based improved coatings, and somehow those sea creatures like what I have forgotten the name, and seaweeds do not like the material. They grow slowly on this paint, so they tried for 3 years, and they found out that they saved about 12–14% of fuel on this one. So they repainted now. The complete fleet of this company is now repainted to improve energy efficiency. There are other developments which going on, but it's still kind of gradual diffusion. Still, this research, especially in condensed matter physics, is driven by some big dream. And the dream is shown by this Samsung advertisement, which came about 10 years ago, and not much has been done, but essentially it's about graphene kind of materials. It would be not graphene, but very likely it could be two-dimensional semiconductors, dichalcogenide. It's making bendable, variable electronics. Many companies are working on this one, including Taiwan Semiconductors, a whole group there, Samsung, a whole institute about this one. So that's a dream. So with this one, I show my final slide. So graphene two-dimensional revolution is going on. There is no question about that. That's very hot research area, continues. I'm very surprised about this because 2007, I wrote a review article which I wanted to finish. Instead of the conclusions, the paragraph should read graphene is dead, because I thought that 3 years after we know everything about graphene, but long-lived graphene, it comes in different incarnations over the last 20 years. In terms of societal impact, it still remains unclear whether this material would be as useful as those niche materials, say tungsten or neodymium, which are somewhere used in our gadgets, like graphene is used in cooling electronics or improving conductivity in the batteries, or maybe one day it will become as important as those materials who support all our technologies these days, like without which we can't live, like silicon, aluminum, and plastics. And with this transparency and my time up, thank you very much for your attention.